This week in quantitative literacy, we'll be playing around with graphing. And we'll do that in a few different ways. So I just want to show some examples. Here I have t-shirt costs. So this winter for Christmas presents, my wife and I made t-shirts for family members based on some artwork by one of our daughters. And to get it all set up to make the t-shirts, we bought some screen printing supplies. It cost about $50 for the supplies. And then for the t-shirts and ink, it was about $15 a shirt. So here's my $50 startup cost. And then you can see if I add 15, I get 65. If I add 15 again, I get 80. So the cost of 2 shirts was about $80. 7 shirts was about 155. And then I told the computer to make a nice graph of that. And you can see since it's going up by 15 per shirt, it rises nice and steady and makes this nice straight line. And this would be an example of what we call a linear equation, which we're going to play with this week. So if we check that out in my notebook here. So Y is my t-shirt cost, and that's going to equal $15 per shirt. And the number of shirts we could call X, and sometimes we'll use different letters for these things. And then no matter what, I get this $50 startup cost for them. And so that could be the equation for that situation there. And if I made 10 shirts, I can just plug 10 into this and figure out this is what it's going to cost to make 10 shirts, given the startup and cost per shirt. Now, graphing something like that, typically to make a decent graph by hand, you need to look at some numbers. So I would need some X's and some Y's, some points to plot. Whoa, mouse is out of control there. So for example, I know that the startup costs are 50 and the cost per shirt is 15. So making one shirt, if I only made one shirt, it would be 15 plus 50. Sorry, my pen's not working so well today. So it'd be $65. And if I made 2 shirts, we add another 15 to that and we get 80 and so on. And we ended up making, how many shirts did we make? I bet we made 15 shirts altogether. So let's see, that's going to be, I think, $275. I better check on my calculator to make sure. Let's make sure I'm not making that up. So 15. And then here I can do the calculation equals, it would be 15 times the number of shirts plus the $50 startup cost. Okay, so that we have 275. And notice it still is on the line that keeps getting projected out there. Now, graphing that by hand, I would need to make 2 axes, 2 number lines. So the Y number line and the X number line. And sometimes when you see graphs, they just make them look like that right there. But, you know, it depends. Like, do you really have negative stuff going on? In this case, I don't. So that wouldn't be the right way to draw it. So it just kind of depends on the situation. Sometimes you need negative numbers, so you might need to see out that way or down here or down here. But in this case, I don't. And then if I'm graphing it by hand, I just have to decide, okay, how should I scale so I can see 0 to 15? And I might do something like 5, 10, 15, which makes the 1 and the 2 hard to see. So then I might decide to do something like maybe 2, 4, 6, 8, 10. And every graph is different. You just got to make that decision when you're making it. Oops. Pen back. So that might be 10 right there. And then this would be 12, 14, 16. So 15 would be right in the middle here. And I don't need to really do every number on there, but professional graphs usually do. But I need to show enough information that somebody can see what the heck I'm talking about. All right, so this might be one way to start labeling this. And then for the vertical one, I got to get from let's see, zero cost is out of the question, right? We start at 50. So the question is, do I even need to go all the way down to zero if I just need to go from 50 to 275? And you might say, well, no. So sometimes what we'll do is we'll break the axis and not even show zero. And that might be shown by crossing that out. Or usually what they do is they just kind of make a little zigzag there to indicate break in the axis. And then I could start with, say, 50 here. And the final project is where you're going to play with designing your own scale. Say if I have to get up to 275, I could do something like going every 50 might be too much if we're only going by 15. So maybe I could do something like 50 and then 70, just go by 20, like below I went by 2. So then this would be what, 90, 110. And these numbers starting to feel a little bit awkward. So I'm thinking maybe I should have started with something like 40 and gone up by 20. And there's no best way to do this. There's just different ways to do it. So I'm going to retrack that and say, maybe it would have been better to do something like 40 to start with, and then go by 20. So 40, 60, 60, 80. So this would be 100 here. And then the question is, with that scale, can I show all the numbers I need to? 120, 40, 60, 80, 200 would be up here. Ooh, that seems too high. 20, 40, 60, 80, 200. No, that's right. Okay, so I can see at the moment, I'm not going to have enough room to get to $275 with the way I chose to scale this. So I got to change my mind and try it again. But once you do decide on the scale, the important things is that horizontally, once I decide that the distance from here to here is 2 units, I got to stick with that, always being 2 units. And vertically, once I decide that this distance here is 20 units, I got to stick with the 20 units. And if it doesn't work out, then I got to erase it and start over and try something else. And so for humans graphing, it's a guess and check kind of thing. And there's no way around it. When spreadsheets and computers do it, they do it a little bit different. So like if we go to the computer and do that, the computer, like when I highlight all of these numbers and say, make me a graph, it looks at the beginning and the end and then makes its best guess at what's a nice range of numbers to show and how to scale in between. Now, we've been using the Desmos scientific calculator, but that doesn't graph. So for this exercise 2.7, lesson 2.7, you might consider using the Desmos graphing calculator, where I can type in something like y equals 15 times x plus 50, and it'll graph it. Now, notice the scale it chose 0 to start with, so that's not an appropriate scale. So sometimes what we'll have to do is click on it and we can move it around. And then we can zoom out. And if that zooming doesn't work, then you can go to the monkey wrench and change things. Like I know I need to get Y up to like 300-ish or 275. So you can just go type that in there and it'll rescale. And I'm not making 60 shirts. So for X, I could go and delete that and say, I'm only going to make like 10 to 20 shirts. And so I can redo how that graph looks to suit my needs. And again, if it doesn't work the way you want, then just go back and edit and try a different number. So maybe I want it to go up to like 350 instead. So we have a little control. And it takes getting used to these tools. You don't really need to use this much. Most of what we are going to do can be done with a scientific calculator and a pencil and paper. Graph paper is nice too. All right, next. The kinds of things we're going to look at for graphs are going to be mostly straight line stuff, like cost per shirt. This is a cool one. Honeybees. It turns out there's a relationship between the distance a honeybee travels to get nectar and pollen to the length of the dance it does to show the other bees where to go. So we've been studying this for a while, and so here's some data I collected, and there's a link here. I'll put the spreadsheet in a link in the video description. But you can see that the distance the bee has to travel and the time of the dance it does to demonstrate to the other bees where to go, it lines up pretty nice. It's amazing. Not everything lines up. If we look at carbon dioxide in the atmosphere over time from like 1960 to 2015, we can see it's increasing, but it's not straight. So I'm not going to teach how to use spreadsheets for this particular lesson, but I'm just going to demonstrate that I can plot points with a spreadsheet and I can tell it to draw a line. And you can see these points don't really line up. In the beginning, they're below, above, then in the middle, they're below, and then they're above again. So that doesn't quite work with a line. So I can say, well, maybe it's something like a quadratic, which we're looking at in this chapter, this lesson, which is a polynomial. Ooh, that looks nice. That hits a lot of points. Another thing we're going to look at is exponential. That doesn't look so good here. This one looks more like polynomial. And sometimes it's pretty cut and dry when something's polynomial, and sometimes it's not. Another example, I like to mountain bike. So here I have a little app on my phone that records my mountain bike rides. And I have the time here and the distance I traveled for each ride. And I ride between like a half an hour and like 3 hours, depending on how much time I have. And then, I go as far as I can. And the trails are a little bit different. So sometimes they're harder to ride because there's a lot of uphill. So there's a little variation, but overall, they kind of line up. And that represents my fitness level, right? I can only bike so far, so fast, given the trails that I bike on. So the bike rides, the times and distances aren't going to be too far from each other in this linear kind of way, which is pretty neat. So this kind of represents my average speed biking. US population. We've been collecting population. US Census Bureau does this every 10 years. So I went out to the Census Bureau and grabbed some population numbers for the United States up to the last census, which was 2020. And these definitely don't line up, right? So if I go here and say, hey, show me a line to go with these points, definitely don't line up, right? Not happening. And then I could say, okay, give me something polynomial is like a quadratic. Oops, wrong one. Well, that's not bad. But generally, populations are exponential in the short term. And, given the age of the human race, 1790 to 2020 is pretty short term. So a lot of experts would say this is kind of exponential, although you can see that we're defying that just a little bit. And there's many ways you can throw an equation at a set of points, and spreadsheets have a lot of that programmed into them. So again, this lesson, we're going to play around with graphing. Mostly it's on a pen and paper, but I wanted to show you some interesting examples on my spreadsheet here that aren't as easy to do as on a pen and paper. But if you take more math, like get into college level math, like statistics, then you'll get to look at these more cool problems. I think they're cool. Other thing we're going to look at graphically is sometimes we have data that's related in a way that's not like a set of points. So for example, the budget for a household. So we have housing costs like rent or mortgage, food costs, utilities, miscellaneous like clothing and medical expenses, maybe entertainment. This is pretty minimal and sparse, but you kind of get the idea, right? We have these different things, these different categories, and we can look at them in a table of numbers, but graphical is pretty powerful for comparisons. And a graphical comparison can either happen in a pie chart like that one or a bar chart, right? Same information, two different graphical displays of data. So we're going to learn a little bit about these in the next lesson. So I hope you have fun this week. Thanks for playing. I'll catch you virtually soon. Bye-bye.